Okay, good afternoon. So many of you are still joining. Okay, so I can't wait anymore. So I'll start because okay. Anyway, last two class we lost because of some meetings, so we could not avoid that. Anyway, all right. So any doubt in previous class? Any doubt? If you have any doubt, you can ask. The cantilever, any doubt? Because already there is a gap of 2 days. Yeah. Any doubt is there? So I think there is no doubt. So let us move forward. Okay. Next, let us take up next topic. Let me go to full screen mode. The last topic of this module. Okay. So we are going to see what is torsion and torsion pendulum and couple per unit twist. Let us try to understand. Let us try to understand what exactly torsion. The action of twisting. So this what exactly? So the action of twist or state of being twisted, especially one end of the object is relative to the other. You are twisting with respect to one end, you are twisting other end. So this is something like a sponge piece. If you twist some shape like this, you can see. So this is nothing but a torsion. This action of twisting, or one end is stationary and twisting the other end, that is also known as torsion. Okay, so now what is torsional pendulum? So to understand this, let us consider wire a wire, okay, for which a heavy object is suspended. So like this, a wire is there, at the bottom a plate, circular plate is suspended. So here also you can see very clearly a circular plate is suspended. So this setup is known as torsional pendulum. The setup is known as torsional pendulum. So in order to call it as pendulum, it should execute oscillation. Maybe a simple harmonic, may not be, but it should oscillate. Okay. So it is a simple harmonic only, but let us try to understand how exactly it oscillates. First thing is, what is torsional pendulum? It's a heavy object. Okay, it's a heavy object suspended from a wire, oscillating about an axis of suspension, which constitutes the torsional pendulum. What exactly that? So whatever I am talking, this wire, here also you can see this wire, for which a object is suspended, attached, heavy object. A thin wire compared to object, you can see a very thin wire, here you can see. So relative to palm, what is the size of the this is a palm size, so same size. So what is a wire you can see here? Okay, very thin, very thin, very thin. So the object is suspended about and which is oscillating. So here what is done? this object is twisted like this about axis, then which executes a oscillation about its axis, suspension axis. So this is known as torsional pendulum. This is known as torsional pendulum. It oscillates like this, to and fro. So if this is a stationary reference line here already marked, so this, so okay, so let me call that as theta. Okay, so when you twist, so this goes up to this point, then come back again, it moves in the opposite direction, goes up to this point, to and fro, but about the suspension axis. Okay, this is known as torsional pendulum. This is known as torsional pendulum. So whenever you twist, there is a torsion. This is a couple, opposing force is acting. That's known as couple per unit twist. It's known as couple per unit twist. What is that? Couple per unit twist. Yes. All right. So that is what exactly defined by generally tau. Sometimes even people use capital C for this, capital C. Okay, so this is a torsion. Okay, it's a torsion. All right, so theta is the angular displacement, angular displacement, or you can also so known as angle of displacement, theta. Okay, so then what is the time period of oscillation of this torsional pendulum? That is given by t is equal to 2 pi into root of L by C, I by C, L by C. Better you take it as I, because it's moment of inertia. Moment of inertia. L, sometimes people take it as L, but L is generally we use it for length, so therefore better to use it for I. C is the couple per unit twist. Small c. Small c is a couple per unit twist. Okay, is it clear? So some of the example for use of this torsional pendulum. This is known as whatever shown is known as torsional spring. Okay, this is known as torsional spring. This is torsional spring. In the same way, you can find the torsional clock, which uses torsional oscillation. Okay, all right. So just now we have seen couple per unit twist. So let us try to get an expression for this couple per unit twist. How exactly you do that? To do that, what we do is, let us consider a cylinder. Let's consider a cylinder of length L. Okay. And let us say A is the radius, small a is the radius of that cylinder. Okay. and which is clamped, Now what we do is, let us say top end, you can see top end which is clamped, and lower end is twisted. Lower end is twisted. So top is fixed, lower end is twisted. How exactly it is twisted? You can see the point B goes to B dash. Point B goes to B dash. So how you can say that? Line OB, line, I mean O dash B. Here it is O dash, this is O, okay? O dash. O dash B is shifted, twisted to OB dash with an angle of twist theta. Theta is the angle of twist. Okay? Theta is the angle of twist. So now, what you can see is, initially the line AB, which is at, I'll take the help of pointer, this line, which is that line A, B, and O and O dash, they are parallel initially, correct? Now, what happened? Now the parallel line shifted to A, AB dash, correct? A, AB dash. While shifting, you can see which forms an angle phi. That is because of twisting couple. Twisting couple. So two forces are acting now. Okay. What is that? One is restoring couple, another is twisting couple. So that is due to elasticity. They are equal. Now they are equal. Equilibrium is established. Otherwise, if you twist, it will twist further. Twist further. But it is not so. You have, due to elasticity, it came to a equilibrium. Okay. Now, if you see carefully, the phi is known as angle of shear. What is that? B A B dash. Angle B A B dash. That's known as angle of shear. That is represented by phi. So now B B dash. Please remember, theta is very small angle. By a small amount it is twisted. It is not twisted by very large amount. So I have given that area of cross section in the above figure. You can see here. So which is a small angle. When theta is small, B B dash can be written as R theta. Agree? Okay. Using this. Okay. Which is at here, whatever our, okay, using this. Okay. B B dash is equal to R theta. Similarly, you can write B B dash is equal to L phi. How you do that? How you do that? That is, you can see here, already I have shown A B dash is equal to phi. A small twist. So if you carefully see, so this is what exactly? Again, this is B B dash. Angle is small. So therefore it is, what is AB? AB is nothing but O dash is equal to L. So AB is also is equal to L. So therefore it is, what is that? Yes, it is L5. It is L5. Okay. All right. Now, so you got BB dash is equal to R theta, BB dash is equal to L5. So therefore equate that. Equate that. R theta is equal to L5. Okay. So you can write the angle of shear phi is equal to, okay, I made a typo error here. It's not X, it should be R. Okay, let us correct that. Using pointer, I will correct. So this is R. So that is phi is equal to R theta. Okay, it's R theta. All right. Let us go to next. So here I wrote it correctly. Okay, phi is equal to R theta by L. R theta by L. All right, let us move forward. We know eta is the coefficient of rigidity or rigidity modulus. Correct? Eta is the coefficient of rigidity or rigidity modulus. Okay. Okay, I will show, no problem. Oh, Vaishali want to see previous slide, I will show. Okay. Once it is done, let me know. I will go to next slide. Okay. Is it clear so far? Any doubt here? Doubt is there? Okay, no doubt. It's clear. All right. So let us move forward. All right. So phi is equal to R theta by L. So now you know coefficient of rigidity or rigidity modulus is defined as, okay, Mayur is asking how BB dash, okay, okay, okay. So, okay, okay, how BB dash is equal to L5, that's what exactly is the question, I think. Okay, no problem. All right. So BB dash is equal to R theta is fine. When theta is small. So important thing is here, the displacement angle is very small. Small twist is given, it is not a large twist. Okay, very small twist is given. So that is why, since theta is small, BB dash is equal to R theta. Okay. Okay. Okay, I just forgot to mention actually. So that's I should have mentioned. I think I missed that. Okay. So this diagram I just skipped, I think. All right. So important thing is, what initially we have considered a short cylinder of length L, radius EA. Okay, clamped at AB. So one end is twisted with respect to other. So before continue that, what you have to assume is this cylinder, okay, short cylinder is made up of large number of concentric hollow cylinders. Concentric hollow cylinder. That's what exactly shown here. First cylinder, second cylinder, third cylinder, fourth cylinder, like that number of cylinders. So for simplicity, what we did is we considered only two cylinders. Okay. One is having, outer cylinder is having radius r. Okay. Then the difference between radius between inner cylinder and outer cylinder is dr. Okay. Okay. The difference in radius. So using this, we wrote bb dash is equal to r theta when theta is small. That is important. Theta is small. That is very, very important. If theta is small only, whatever assumption is valid. Okay. In the same way, here if theta is small, phi is also small because this displacement is small, bb dash is small. Then automatically this angle is also become small. So therefore, considering this, which is at triangle BAB dash. When phi is small, you can write BB dash is equal to L phi. Because OO dash is L, similarly BA is also L. Okay. So therefore you can write BB dash is equal to L phi. Okay. So therefore r theta is equal to L phi, phi is equal to r theta by L. Okay. Okay. So I think that is clear. Now, our intention is to find out expression for couple per unit twist. Couple per unit twist. So, eta is equal to coefficient of rigidity or rigidity modulus. Okay. So therefore, eta is defined as shear per tangential stress, that is force, okay, by shear strain. Shear is nothing but a force only. Okay. So you can write eta is equal to T by phi, because phi is the shear strain. Phi is the shear strain. What is the amount of shear is it? It's phi, correct? So it is shear strain. So if you recall whatever original dimension because of tangential stress, so this is similar to tangential stress only. This end is fixed. For this end, the force is acting. Okay, so T by phi. So therefore you can write T by phi as T is equal to eta into phi. That's equal to, what is phi? Phi is r theta by L. So therefore eta phi is equal to eta into r theta by L. What is the face area of hollow cylinder? That's what exactly here. This is a face. Whatever I have shown the figure at the top, that is a face. So we consider a hollow cylinder having radius r. So therefore face area of the hollow cylinder, face area of this hollow cylinder, whatever we have considered, inner and outer, so face area is 2 pi r, this is the only face, small, this whatever between two circle, whatever area you find, that is the face area, 2 pi r into dr. Okay. So therefore, total shearing force on this area, total shearing force on this area can be written as face area. So if you want how exactly it came, that's because force is equal to stress into area, that's equal to T into area, correct? So total shearing force you want, force is equal to stress into area, stress is nothing but T into area. T we found out, that is eta into r theta by L. This is what exactly? Area just now we have written, that is 2 pi r dr. So on simplification you can write it as 2 pi eta theta divided by L r square dr. Is it okay? Alright. Okay. Shall I go to next slide? Or still you are making a notes? Okay, I will move to next slide. So momentum of force about OO dash, that can be written as 2 pi eta theta L r square dr into r to radius. So therefore you can write on simplification, you will get 2 pi eta theta divided by L r cube into dr. So what about this? This is just for one hollow cylinder having an outer radius r and there is a thickness dr. Okay, thickness of the cylinder is dr. So this is moment of force about a single cylinder. If you want to find out the twist couple applied to whole cylinder, so for that you have to integrate this moment of force about a single cylinder, about OO dash of a single cylinder, from limit r is equal to 0 to r is equal to a. Maximum radius of the cylinder is a. So therefore, starting from 0, starting radius 0, if you integrate all possible hollow cylinder you can get, not only that, you will get momentum of the force of the each cylinder. If you integrate that, you will get couple, twisting couple applied to whole cylinder. So therefore, twisting couple C is equal to 2 pi eta theta divided by L. Okay, that's a constant. We want to integrate with respect to r, so therefore you kept it outside. Okay, all right. System is responding a bit slowly. Okay, this is a constant. Then from where to where you have to integrate, that is starting from radius 0 to maximum, that is integration from 0 to a, r cube dr, that's equal to 2 pi eta theta by L on integration r cube, you will get r to the power 4 by 4. Okay, right. So integrate that. Integrate that. Integrating. So putting the limit. Putting the limit. So putting the limit, you will get the values. So okay, my system is, I think, hanged. Can your screen is changing? Is your screen is changing? No, right? You got C or tau, right? Ah, it's came. All right. Now it's coming. Okay, okay. All right. So, if you substitute the limit, okay, what do you get? 2 pi eta theta is divided by L, a to the power 4 divided by 4. Because lower limit is 0, so therefore numerator is 0, so only your thing left is for higher limit, so therefore a to the power 4 by 4. So 2 will get cancelled, so you are left with 5 into eta theta a to the power 4 by 2l. Okay, so therefore tau twisting couple per unit twist. Uh, this is not couple per unit twist. I'll make it clear. So here, take a pointer. Couple per unit twist is C. Okay, this is twisting couple. Okay, so therefore tau is equal to whatever pi into eta theta divided by 2l, we call it as twisting couple. Twisting couple. That is written as couple per unit twist, that is pi eta a to the power 4 divided by 2l, giving twisting couple per unit twist, angular twist of the wire. Angular twist of the wire. That's what exactly expression for couple per unit twist. Couple per unit twist. So this is the expression for twisting couple. Tau or capital C. Be careful. If you write C, this is a capital C. This is a small c. Okay. Is it okay? Have you noted down? Okay. All right. Now let us see what are the applications of torsional pendulum. Application of torsional pendulum. The first application, working of torsional pendulum clock is based on torsional oscillation. So you might have seen this torsional clock. So here, so there are two types of what is that? Clock you might have seen. One is clock with simple pendulum. Simple pendulum means okay, I'll take a pointer. Simple pendulum means in the clock, if this is the clock, okay, this is the pendulum, okay, oscillate like this, correct? To and fro oscillation. Whereas here, torsional pendulum means, so there will be, pendulum like this. This is the pendulum which will oscillate, torsional oscillation like this, about axis. Here will oscillate like this. Circular motion it will have. Okay. All right. The next possible application is uh, what is that? This is used to characterize some of the polymers. Okay. Then determination of frictional force between solid surface and flowing liquid environment using forced torsion pendulums. Forced torsional pendulums. Another possible application is torsion spring. It's used in torsion clock only, whatever just now we have seen. Even your clothespins, which is clothespin or hand binding clips. So, okay, hand binding clips also works under the principle of torsional oscillation. Okay, okay, where is that? Okay, this is what exactly torsion spring. Torsion spring. When I apply force again, it restores. Again, it restores. This is what exactly torsional pendulum. Okay, and couple per unit twist. Any doubt? Any doubt? With this, we have completed this topic. Okay, so let us I will change the PPT. We'll go to one more PPT. We have to work out problems. Okay, last slide. You can see, right? We are in the last slide only. Application or previous slide? Rahul. Rahul, which slide you want? Application slide or previous one? Previous slide, okay. Is this one? This slide? Okay, okay. So you can copy that. Meantime, I will open another slide. All right. So I will stop sharing this slide. Done, right? Shall I stop? I'll go to another slide. Okay, stop sharing. Now, okay, I'll share one more slide. Okay, 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 okay. Okay. Okay, can you see this? I hope you can see this. Okay, before getting into um, problem solving, just I will summarize whatever we have seen so far. Okay, so in a single slide, so you have seen basic definition of elasticity, what is stress, what is strain, and type of stress, type of strain. Okay, stress is force per unit area, strain we have defined it as, what is that? Change in length or dimension or volume to the original length or dimension or volume. So which gives certain formula, you can see here. Carefully see the slide. So everything is summarized. So this slide is very useful. So to work out the problem, I have listed all problems. Correct? So stress is force per unit area, or okay, this is formula for stress. Similarly, strain, different type of strain is there. Change in length or dimension, volume to the original length or dimension or volume. So next, Hooke's law. Stress is directly proportional to strain. So that we have seen. Then we have seen stress strain curve explanation. Plot plus explanation we have seen. So this is very important. Please remember. So these basic definitions are asked in the examination. In the same way, stress strain curve is also asked. So I am going to share question bank today. Okay, in the Google Classroom I will share. Stress strain curve, plot plus explanation is required. Alright. So based on the Hooke's law, notes also I will share, Mayur. I will share the notes also. Okay. I think I missed that. Okay, alright. Thank you for reminding me. So I will share the notes. So, alright. Stress by strain, which is a constant. It's a constant. So that is elastic constant. So there are different types of elastic constants. We have studied that. What is that? Young's modulus, that is longitudinal stress by linear strain. Rigidity modulus, that is shear or tangential stress by shear strain. Shear strain. Similarly, bulk modulus, that is volume stress by volume strain. Okay. In the same way, we have defined a Poisson's ratio, that is sigma is equal to beta by alpha. What is that? longitudinal strain by lateral strain by longitudinal strain. Alpha is longitudinal strain, beta is lateral strain. Okay, longitudinal, lateral strain, and different elastic modulus we have done. Then we have seen the relationship between all modulus, different relationship. K is equal to 1 by 3 alpha minus 2 beta, that is relation between K and alpha and beta. Similarly, K is equal to Y by 3 into 1 by 2, 1 minus 2 sigma, relationship between K, Y and sigma. Next we have seen relationship between eta, alpha, beta. Eta is equal to 1 by 2 into alpha plus beta. Similarly, eta is equal to Y by 2 to 1 plus sigma. In the same manner, we have seen 9 by Y is equal to 1 by K plus 1 by 3 by eta, or sigma is equal to 3K minus 2 eta divided by 2 eta plus 6K. So we have seen practical limits of Poisson's ratio, then strain hardening, strain softening explanation we have seen, effect of stress, temperature, annealing, impurity on elasticity, etc. we have seen. So this also question may arise. So this summary slide almost covers all the possible question also. Beams, we have seen neutral surface, bending moment, type of beam, definition with diagram, bending moment, and derivation. All these things we have seen. Okay. And I think, okay. All right. So that you have seen. Next, the bending moment, different types of beam we have seen, expression we have seen. And then we have seen cantilever. Then today, so sorry for accidentally it is muted. Okay, these are the important expression in bending moment. Similarly, cantilever, these are the important expressions. So these are the important expression in torsion. So these are required for problem solving. Important. Okay, is it okay? Okay, so we will do the problem solving in next class. So now it's, I think we'll take the attendance poll. Already many are left the class, I can see that. There'll be 1 minute time. Okay. All right. Your poll is open. Attendance poll. Once attendance poll is complete, you can leave the class. No problem. So thank you for joining the class. So ending the class. I'll stop sharing this. Anybody want to see this? You want the slide? If you want, I will wait. Otherwise, I will close the stop sharing. Shall I stop sharing? Okay, I'll stop sharing. Thank you. Thank you for joining the class. If anybody want to ask anything, you can unmute yourself and ask if you want to ask something.